Hi guys, welcome to Learning Electronics Repair. Today we're going to build a fun circuit to demonstrate a serious matter. This is important. So we have on the desk here two components. We have a bridge rectifier and we have a capacitor. So this is basically what you find on the input to mains powered equipment for the main part. Power supplies, switch mode supplies, that sort of thing. Battery chargers and stuff that runs directly from the mains. So at the input of the circuit after the mains goes in, you'll normally have a fuse, NTC thermistor that prevents too much current rushing in. And the reason it would rush in is because when you apply the power, this capacitor, we'll use this one, so this is a 450 volt, 150 microfarad, is discharged. There's no charge in it, and that thing wants to charge up as fast as it possibly can. And as fast as it possibly can is pretty much instantaneously. So that means that when you power the equipment up, you get a big surge of current going into here while it charges. And that big surge of current can blow, for example, the bridge rectifier. So this is in front of the capacitor, and this is converting the AC coming in to DC. Okay, so this is why we have what's called an NTC resistor, which starts off at a relatively high value, maybe tens of ohms. As the current comes in, that restricts the current, but it warms up, and as it warms up, it decreases in value. So that's what we have. We have some filters and capacitors, but to demonstrate what I'm going to do today, we only need these two components. And what we're going to do is look at how to discharge capacitors. Okay, how to discharge these capacitors safely. So first of all, why do we need to discharge the capacitor? Okay, well, let's just draw this on a bit of paper and then let's try. So your power supply or similar device will have a circuit like this. This is your mains coming in, live, neutral. Yes, we'll have this NTC thing I mentioned in a lot of cases, and some capacitors across here and inductors to filter noise, but they're not important. This then goes into the bridge rectifier. So this connects to the AC coming in. In my case, this is 220 volts AC, or thereabouts, okay, plus or minus. Coming out of the bridge rectifier is DC. Well, this is not a smooth DC. The way this bridge rectifier works, very briefly, because I've done this before, is we have an AC signal coming in, like so, yeah. 50 hertz, 60 hertz, depending on your mains frequency. And coming out of here, effectively, this line, by the way, is 0 volts. If you wondered why I drew a line, we have this. We have pulses like this. And these pulses effectively are the same as this, but that part of it, the waveform, and because this is 0 volts, this is plus, this is minus, the bridge rectifier inverts this part and puts it in here. Okay? So that's why we get only the positive pulses. And because he puts it in here, okay, if you think about it, the frequency of these is twice the frequency of this. Okay, so if this is 50 hertz, this is 100 hertz. And obviously if you're on a 60 hertz main, this is 120, okay? So that's basically what the bridge rectifier does. But our device generally does not want this pulsed DC. It wants a smooth DC. So to get that, we put a capacitor here. Okay, and this is the large capacitor I showed you, in my case 400 volts and 150 microfarads. That's a simple design. For efficiency on modern electronics with power supplies above a few hundred watts, there will actually be a boost converter in here. It makes the circuit more complicated, that boosts the voltage into the capacitor, but that's not relevant for what we're doing today. All I will say is if it has the boost, which is known as PFC, the voltage in the capacitor will be even higher. Okay, with this circuit, the voltage in the capacitor will be about 320 volts if this is 220. Now you might wonder why, how and why do you get 320 volts DC out of 220 volts AC? Well, this 220 volts refers to something called RMS, root mean square. If you don't want to worry about the mathematics, think of it as a kind of average. So it's a kind of average voltage between 0 and the peak. Sort of there. It's not in the middle. Okay, it's sort of there. It's about 63% of the way up, but it doesn't really matter. So that 220 refers to that. But this capacitor will charge up to the peak voltage, which is this. Okay, and the peak, as you can see, is more than the RMS. So that's why we get 320 volts. Yeah. If we had that PFC I mentioned, the booster, the capacitor will have 380 to 400 volts. Usually. Okay, so that's what the circuit is. Now, why do we need to discharge the capacitor if we're working on this? Well, generally speaking, if the device is working, then connected to here is a load. The load could be something, you know, like a physical load, like a motor or a heater. Or it can just be an electronic device like a switch mode power supply that drops the voltage to a lower voltage. But regardless of what it is a load. And the bridge rectifier on these pulses is feeding voltage into the capacitor, and the load is taking voltage out of the capacitor. Yeah. So while the device is running, while it's working, you just maintain a steady voltage here. If you switch this off, the bridge rectifier is no longer charging the capacitor, okay? But the capacitor is still discharging. So what will happen when you switch off in a fairly short amount of time? The load will discharge the capacitor to a safe value. You may think it will discharge it to 0, and it might discharge it to 0, but it depends somewhat on the type of load. Some circuits will discharge the capacitor down to, say, 70 or 80 volts and then stop running and stop drawing power. So this will drop down from 320 to about 80, and that will stay at 80. And the reason it stays at 80 is because the load is no longer drawing any power. Yeah? Now, the chances of you trying to work on this, it's probably faulty. It's probably faulty, that's why you're trying to work on it. And if the fault is such that the load draws no power, yeah, so there's no short circuit, there's nothing going pop, it's just literally the load is like open circuit, it's not drawing any power at all. What's going to happen is this capacitor is going to charge up to 320 volts, or more if you're unlucky, and it's not going to discharge when you unplug this. And technically speaking, with no load, that will stay charged forever. Okay, now forever is a rather bold statement, and nothing in the universe is perfect. Have you noticed that, by the way? Nothing in the universe is perfect, yeah? I think that makes itself evident every day. And the same with this capacitor in this circuit. The capacitor itself will have some internal series resistance, like across here. And that effectively acts like a leakage resistor. So a very small current will flow through here, and eventually that will discharge. It could take a long time, but it will eventually discharge. But the chances are we want to work on this before eventually. So we have to discharge the capacitor. Now I'm going to show you 4 ways to do it. 2 ways are definitely not the way to do it, and 2 ways are the way to do it. Okay? So to do this, we're going to make a little device, and you can discharge these capacitors perfectly safely. Okay? Everything is better, of course, not on paper. but in the real life imperfect universe. So let's build this circuit. Let's have a look at the voltage we have in this capacitor, and then let's look at the various ways we can discharge this. To do this, we need one more component. There, we probably need a couple bits of wire as well. And we should test these components because these are poles. These have been salvaged from equipment. Yeah, so let's just test these before we start. So first of all, the capacitor. So I'm in capacitance range. The multimeter will do this. It's just a bit slow, but never mind. It's probably what you have. And it tells us our capacitor is 135.9 microfarads. These things are never very close tolerance, by the way, so that is perfectly fine. The bridge rectifier, this is easy to test as well. We go to diode mode. And if we put the red lead on both of the AC terminals, we should see a diode junction to the positive. So black on positive, red on AC, there's a diode junction, there's a diode junction, okay, and then the other way around, with the black on the AC, we're feeding negative in now, red on the minus terminal, diode, and then across the bridge rectifier itself, in the reverse direction, with so the red lead to the negative, we'll see like two diodes in series. There. Yeah, 900, roughly two diodes in series. 4, 5, 0 times 2. And the other way around, with the red to the positive, it will read open. So the bridge rectifier is good, the capacitor is good. Now let's build this. And there is my test circuit. So the blue and brown wires, this is your live and neutral, although in the EU, seen as the plug will go in any way round, you don't actually know which is which, but it doesn't matter, okay, because it's AC, so there is no polarity. We then have white and black going to our capacitor. We have the black on the negative, it's marked, the white is the positive, okay. And you can see on the bridge rectifier, the AC goes into the AC terminals, negative end of the bridge rectifier to negative end of the capacitor, and positive end to positive end. So that's our test circuit. Now I'm not going to plug this directly into the mains. I could do. I'm going to connect it via a light bulb. This is called a dim light tester or current limiter. I'll link this video to the one that I built. I'll show you how to build these. There's two reasons for this. In my circuit, I don't have the NTC. But the light bulb will basically do the same thing, so it does three things. Okay, one thing it does is prevent too much current flowing into the circuit. Because the bulb will have a resistance, yeah? There. So first of all, it stops too much current rushing in and blowing the bridge rectifier when you first power up as this charges. Secondly, if there's a short circuit somewhere here, once we short it, it's just like connecting the light bulb across the mains. It won't go bang, nothing dramatic will happen. The light bulb will come on bright, okay? And the third thing is, when we first connect this up, current is going to flow to charge the capacitor. So this light bulb should flash or come on bright, then go dim as this charges up. So it's a very good visual indication when you're working on stuff. Connect a light bulb like this, and this is a mains light bulb, so 220 volt. And by the way, this is not an LED, it's not a fluorescent. This is a proper filament light bulb. You can use a halogen one or just a standard filament bulb. Yeah, I know they can be a bit hard to find, but get yourself one. Yeah, you can certainly buy them online, that isn't a problem. Wattage wise, I on this tester have a 65 watt bulb in there. Actually no, I think it's 72 watt. So that's a fairly low wattage depending on what you're working on. You might want to put a higher wattage in, but that's okay for what we're doing. So let's connect this up, let's have a look at the light bulb and let's see what happens. And there is the light bulb, okay, over there, a mains light bulb. Just remember, guys, electricity at high voltages can be dangerous. Inherently, it is dangerous. It only becomes safer when you understand what you're doing. But that's really the purpose of this video anyway, okay? So we'll put the meter onto AC. I'll use this one because it has a nice bright display. You can see it easily. So AC volts, okay? And I'm going to measure across the two AC terminals. By the way, safest way to do this is to hold the probes in one hand. Then if something goes wrong, like you have a broken meter probe, it's not going to connect you to the high voltage between the two hands, because if that happens, the electricity is going to go up one arm, across your chest and down the other. And that's the most dangerous thing that can happen. Hearts don't like high voltage, yeah? It might just stop. So a safer way, if you can do it, I mean, obviously consider the situation, but if possible, hold the meter probes like this with one hand, okay? Now we're going to switch on and watch the light bulb and see what happens. See, it flashed and went out. And we have 226 volts here. That's my 220 volts mains, okay? If I go to DC and we measure across the capacitor, again, I'm going to use one hand to do this if I can. It's safer. We have 315 volts. Okay. Now I'm going to turn the power off. Watch. The capacitor's discharging. Yeah. Slowly. Okay. It is discharging, but that is going to hold a nasty, dangerous voltage for a long time. Now you'll notice I'm measuring across the bridge rectifier. I can also, and I'm going to use two hands, but it's easier and less dangerous to hold on this. Go to the capacitor. And I know I have good meter leads. We still have 300 volts. So I can measure across the capacitor, or I can measure across the bridge rectifier. Don't think you can do this when you're working on a device in circuit. It's possible and definite if you have this PFC, this booster circuit, that there's a diode in between the bridge rectifier and the capacitor. And when you measure across the bridge rectifier with it switched off, you'll see no volts. You go to the capacitor, you'll have 380 probably. So always measure across the capacitor, unless you really understand the circuit and you know what you're doing, okay? Now, we need to discharge this capacitor, and there's various ways we can do it. The first way is the way you should not do this, okay? I'm not going to do it right here because I have one I prepared earlier. So here is a clip from a video I published about 2 years ago. On the low voltage side. Ow! And there was some charge in the capacitor. So you can see, guys, you can discharge a capacitor with your finger. Yeah, don't. Not only is it very painful, but it may kill you. Yeah, I was lucky then. Notice I was holding the thing with one hand. My other hand was nowhere near. It wasn't connected to anything grounded or anything else in the circuit. So the current went through a finger. It didn't come across me. If it had come across me, that could have been fatal. Okay, so yeah, you might think it's funny. Yeah, amusing, but if it gets you, you won't think it's funny when you're lying on the floor with your heart stopped, okay? Right, so that's how not to do it. Our capacitor, by the way, while we've been watching that, still has 287 volts in it, okay? The second way not to do this, the screwdriver method, yeah? So it's switched off at the mains. I can short out the capacitor with a screwdriver, yeah? Okay? You like that? It even made me jump, yeah? So I can do that. Let's go to our capacitor. Oh, it's certainly discharged. Yeah. Right, that is not good for your screwdriver. It's not good for you if you happen to pick up a screwdriver where the metal shaft comes all the way through to the end, yeah, or a wooden one that's wet. So don't do it, guys. It's not good for you. You probably need a new pair of trousers if you did it accidentally. And to be honest, it's no good for the capacitor. When I do that, all that current that flows through my screwdriver to discharge the capacitor also flows through the dielectric, the insulation barrier inside the capacitor. So that dielectric was subjected to an extremely high current. And usually the thing will survive, but do it enough times and it won't, okay? So it's bad for the tools, it's bad for the capacitor, and it's possibly bad for your underwear, okay? But it did discharge. Have you noticed, by the way, it's come back a bit? Capacitors have this ability, this recovery ability, whereas the voltage will kind of like bounce back up again. It won't go very high, by the way. It won't go up to a high voltage again, but they will kind of like recover like this, especially if there was a high voltage in there to start off with. Yeah? Okay. So that's the second method. Don't do it. Oh, and similar to the screwdriver is this method. Yeah, it is discharged at the moment. Don't do that either, because almost certainly there's going to be some metalwork here and you can slip, and you might have a pair of pliers like this that are worn. You'll soon connect yourself to a high voltage. Don't do it. Again, it's bad for the tools and bad for the capacitor. Okay, so to a method that you can use, and that's this one. So this is to use a high value resistor. When I say high value, this is an 18k resistor. This is too high, really. I would usually use 2.7k or 3.3k and use the resistor to discharge the capacitor, okay? Now, this works. I'm going to show you. Because I'm using such a high value, it'll take a little while for this to discharge. But because I want to show you that, I'm going to connect the meter using some crocodile clip leads. Notice it's recovered up to about 8.5 volts now. Yeah, I told you it would recover. So we're on DC volts again. We're going to charge the capacitor up, and then we're going to use this to discharge it just by holding the resistor against the terminals, okay? And we'll see on the meter. In fact, look, I've just done it's gone down to 5.4, yeah. Okay. Right, let's power this up. 312 volts. Switch off. Okay. So we'll take our resistor. And look, it's discharging. Takes a little while. A lower value resistor would be a bit faster. I was, as I say, use a 3.3 or something like that. Okay. Sometimes I'm not making a very good contact, which is why it stops discharging. Yeah. We're basically down to 0 now. Take it off. See the recovery? Yeah. But recover a bit. Okay, so that is a safe-ish way to do it. It's safe enough for the capacitor. It's safe enough for the resistor. The only problem with this is you're holding your hand fairly close to the high voltage. You could effectively like stick this onto something like a lollipop stick, something of that ilk, something plastic maybe. Yeah. Glue it onto something. That's safer. Yeah, so if you want to use this method, I suggest you glue the resistor onto something like this and hold it a bit further back. And you can also cut the legs a little bit shorter then, because you don't want these bending and touching. But that is a safe, pretty much way to do it, okay? Now let's look at the best ways. Okay, the third way. This is my favourite way, by the way, at the moment. So I've taken a multimeter. just an El Cheapo multimeter, the cheapest one you can find, even cheaper than this one, okay, as long as it measures DC volts. And I've connected a resistor directly across the meter. This is the 3K3 resistor, 3.3K, 5 watt. You want to use a reasonably high wattage resistance for this, because when you first discharge the capacitor, especially with a lower value, some current will flow. If you don't have anything like a 5 watt resistor, you could, for example, do something like this. And put something like a 330 ohm and 5 of them in series. And use 1 watt resistors, and that's the equivalent, close enough of that, yeah, not far off. Remember, none of this is critical. So you could do something like that if you haven't got any high wattage resistors. And you saw yourself an 18K work, so it's not that important, just don't go too low in value. That's wired across the meter, and now I have my 2 meter probes, which are meant for measuring high voltage anyway, so they are relatively safe for doing so. And I'll show you how I actually did that. So this is the resistor, you see, 3K3, 5 watt. And what I've done is I've taken 2 old bent meter probes. I cut the leads off here, soldered the ends together, and then connected the resistor. A bit of heat shrink on there, so it's safe, you can't touch that really, not easily. And then these can go into the meter. Okay, these just go into the meter. So I haven't actually modified the multimeter in any way, I've just modified an old set of leads. Common volts. So what I can do with this now, switch this on, go to DC volts. Okay, auto DC, I'm on DC volts, I can put the light on if I want. Okay, and let's use this to discharge our capacitor. Again, we can see the light bulb, so we know our capacitor is charged. Yeah, it's charged. Switch it off, it's off now. You don't want to be discharging this while it's switched on, by the way. It's not going to discharge, but the resistor will eventually get hot. We now connect across here. And you can see the voltage. Yeah. In fact, the voltage drops faster than this meter can actually react because it's on auto range. You'll see it better on the other meter. So I've just plugged the thing in, okay. Once again, capacitor's charged. Switch her off. 30, 24, 6, 3. You can see that discharge is much faster because it's a lower value resistor, but there's no sparks, there's no drama. And the multimeter is telling us it's discharged. And because we have the multimeter, charge it back up again. If I happen to just go backwards across the capacitor, I just see a negative voltage, but I still see a voltage. Yeah, I still see what voltage is in the capacitor. Okay. Because I'm lazy and because I know full well if I make this set of leads up, sooner or later I'm going to forget to be connected to my multimeter when I don't want to discharge something, and something bad could happen. Yeah, so that's why I use just this little meter. I don't use it for anything else, it's just there as a capacitor discharger. That, I think, is the best way to do it. But what if you don't have an old multimeter lying around? Well, we could make a discharger using a resistor like we are doing, with an LED indicator on, so the LED lights up until the capacitor discharges, then it goes out. Now there's a couple of things we need to consider, so let's go back to the paper and let's plan this. Now you may think this is easy, so you just take a resistor, an LED, okay, and this is where you connect your meter probes or whatever else you use to connect to your capacitor, and you can discharge it with this. Now there's a couple of issues here. First of all, if you did that, you've got to choose a resistor of high enough value so that the current flowing through the LED is not too much to blow the LED. But if the current's low, you can't discharge the capacitor in any reasonable amount of time. So that's the first problem. What value is the resistor we use? Second problem, if you connect this back to front, the capacitor won't discharge. The LED won't light up either. So you'll think, oh, there's no voltage in that until you touch it. Yeah. So that's the problem. So we need a bit of a cleverer way to do this. And this is how we do it. So we take a meter probe, as I said. We take a resistor and we'll use something like, let's use that 18k resistor we had because it's what I have handy. Okay. And then we connect that to some diodes, not LEDs. Let's take 4 of them. Okay. And we connect this down to the other probe for discharging. Okay. And these are just normal silicon diodes. We'll use something like 1N4007 because they're readily available. These are 1000 volt, 1 amp. And if we connect 4 in series like this, each one will have a voltage drop and we can measure it. And here is the diode. So we put the meter into diode mode. Okay, we measure it. And it's reading 0.57. Okay, actually, as you pass more current through, that will go down a little bit. But let's say 0.55. Okay, just a nice round number-ish. So if I put 4 of these diodes in series, what I will actually have across the 4 is about 2.2 volts. We can try that. And there is my little chain of diodes. You don't need to use this particular one, by the way. Anything that'll handle like 400 volts, 1 amp or something, fairly common rectifier diodes, you can use them. Let's see if we can measure the voltage drop across this with our multimeter. Well, it's actually a bit too high for the meter to read. So you'll see one diode reads 0.56, 2 of them 1.11, 1.63, and that one is just too much. But if I read from here to here, 1.11. So you see the total's about 2.22. Now, the reason for this is that regardless of the voltage that's in the capacitor, which is discharging, the voltage drop from here to here will stay the same until the voltage gets so low that it's below the 2.2 basically. So it doesn't matter so much what voltage in here, the voltage there with respect to there will stay the same or close to. So what we can do now is we can take our LED and a resistor, it needs a resistor, okay, here's our LED, and connect it like that. Now we can calculate the value of this resistor because we know the voltage here is always 2.22. Yeah, so we can sensibly calculate a resistor. Let's do it. And we could calculate this ourselves, or we can cheat and use one of these online calculators. So we need to know the supply voltage. Well, we know what it is now. We didn't before because it could have been anything, yeah, as the capacitor discharges. But now we know it is 2.22 volts. We also need to know the forward voltage of the LED, okay? We'll use a red one because red A is warning and B has the lowest voltage drop. So here is a red LED, at least I think it is. Let's try it. It should light up so we know it's good and we should see the voltage drop. And it's 1.75 and it is red and it does light up. So 1.75. Again, that will change a little bit as the current changes, but it's close enough. Good enough for Gran Canaria, yeah? Somebody laughing in the background. 1.75. Now, how much current through our LED? Well, 5 milliamps seems reasonable to me. Okay, so we'll put 5 in there. It's set to milliamps, and the resistor value equals 94 ohms. Now, we can't get a 94 ohm resistor. We could get a 92 ohm, or we get a 100. Let's have a 100. Yeah, close enough. So our resistor is 100 ohms. Again, not particularly critical because the LED could take less than 5 milliamps and light up with like 1 milliamp, and it could take 20 and light up. Well, that's fair enough. Okay. So we need to build this, but remember, if we put the leads on the capacitor the wrong way around, it won't light up, and we need it to. So what we also need to do is build the same circuit over here the other way around. Like so, and of course another LED. And resistor. 100R LED. Okay, so that's it. I need to put this together in such a way that it's safe, so with some heat shrink. So let me build this and then let's try it. Okay, and there I have them made up. This one, I actually put a piece of heat shrink over the resistor. You can see it on this. When I left this light, you can see it. It's safe enough. I'm going to put some heat shrink over the whole thing with a hole cut where the LED comes through. Now you might think, and I'll just mention this, that there should be maybe another diode in series with the LED, so that when you connect it in the reverse polarity, the LED, which is reversed, doesn't have a reverse voltage across it, so to speak. But remember, this is never more than 2.2 volts, so you can easily put that sort of voltage across an LED in reverse direction. It just won't light up, but it won't do any harm, and there's a resistor there to limit the current anyway. We can test these. So I have my bench power supply set here, you can see, and I've set it to constant current, 150 milliamps. Okay, so I'm just shorting the leads together. I get 150 milliamps. So I can connect this across one of these now. The LED lights up and we get 150 milliamps. But that's not passing through the LED, otherwise the LED would burn up, as you know. It's quite happy because the voltage across here is, well, you can see the meter saying about 3 volts, and that includes the voltage drop across the leads. And if I change the voltage on the power supply up to the maximum of 32 volts, it's fine. If I turn it down, eventually get it low, so it's about 1.6 volts the LED goes out. Okay, and otherwise it's constant brightness. So that's exactly what we want. Just try the other one. Yeah, just turn the power up. Yeah. Stays a constant voltage, constant current, even though I'm turning the power supply up to maximum. Okay, so we now need to wire these back to back across each other. Okay guys, so that's put together. So we have the 18k resistor here, 5 watt. We have the 2 LEDs, the wired as I showed you with the 1M4007s, 4 in series across each one, and then the 100 ohm resistors. I have this connected to my bench power supply, so if we turn the voltage up, one of the LEDs should light up. Yeah, that one. So that's lighting up at about 2.5 volts. It reaches full brightness at about 10 volts, and then it doesn't really affect it much after that. Okay, so you can see that one. And if I now reverse the polarity on here, okay, the other LED is lit up, and again I can turn the voltage up to 32, I can turn it down. At this point, yeah, about 2.5 it goes out. Okay, so that's working as we would expect. Now let's try to discharge our capacitor with it. And here is our capacitor. There's a little bit of voltage in, not much. I have the multimeter attached so we can see how quickly this actually discharges. This is my discharger. So power on, light bulb goes out, so there's voltage in there. And then we'll connect this across our capacitor. So this is with the red lead to positive. And the LED comes on. You can see the voltage dropping away on the meter. We'll do a discharge just the same. We don't need the meter. That's just to give us an idea of what's happening. We can disconnect the meter now. It's absolutely fine. It will still discharge. We're down around 4 volts and the LED is going out. It's about 2.5. What we expected. Okay, we power it up again. Charge up again. And we go the opposite way. So red to the negative this time. Other LED comes on. It's discharging safely. And there it is. It goes out at about 2.5 volts. So that's our discharger. This works just great. We no longer need the multimeter. And we can still discharge our capacitor safely. So once again, bulb came on. I know it's charged. Come on with this. Red LED, and then just wait. This resistor is at 18k, as you know, it's a little bit slow. I would suggest you probably go for something like a 10k, sort of between 5 and 10, maybe a 4.7, something like that, and it'll discharge that bit quicker. But we can see this works just great. Okay, so that's why and how you should discharge capacitors. Hopefully this will make this safer for some of you out there, that you understand this better, okay, and you feel more comfortable on this sort of work. Remember, it's not dangerous unless you don't understand what you're doing, unless you don't pay attention, okay. So there you go, nice simple device, either this one or the cheap multimeter, whichever you prefer. They both do the job just fine. Hope you like that. Get into the comments below, let me know down there. Maybe you have a different way to do it, maybe you have a better idea. This is the ghetto way, I think, but it was certainly cheap, yeah. I'm always interested, of course, to know what you guys think. Okay, thanks for watching, and I look forward to seeing you all soon again on Learn Electronics Repair. Ciao for now, guys.